previous speakers who have done a lot of the work in introducing the topic that I'd like to talk about today, so I can kind of cut right to the chase almost. But before I do that, we've heard many iterations of different ideas about using Floquet driving to change the properties of quantum systems. So I just want to take some time and lay out the different kind of Floquet strategies that we've heard and contrast them a little bit, so we can really emphasize the angle that I want to make on Floquet driving. So what we heard a lot in the first half of the conference was this idea of using Floquet driving to create new stable steady states that could have occurred ordinarily, but maybe you didn't have the right terms in your Hamiltonian to realize them. So if I just draw a simple pendulum hanging from a knob, it has one stable equilibrium fixed point down. But if I periodically drive strong enough, I can turn the upside down pendulum into a stable fixed point. And the thing is that I could have, since I'm a theorist, I could have equally well made a different kind of force by just flipping the sign of the gravitational constant, which pointed up. And then this would be a perfectly valid equilibrium stable fixed point, even without the driving. Yeah. Okay, so the point is we can use, one way to use Floquet driving is to use a periodically driven forces to induce new effective time average forces and create a new but effectively equilibrium steady state. So what we've heard about in the last couple of talks and what I want to do in this talk is quite different, which is to look at not at the static steady points, but at new dynamical properties of Floquet systems that arise from driving that couldn't occur in any static equilibrium. So for example, if we take the same pendulum without driving and poke it a little bit, it'll kind of oscillate at its natural frequency, and those oscillations will die down until it goes back to its steady state. On the other hand, if we drive it and drive it strongly enough, it can undergo some bifurcation where it develops persistent oscillations at twice the period of the driving. And this kind of period doubling in this example, and we heard a quantum mechanical version of this in the last talk, is a purely dynamical phenomena. It's something that simply doesn't exist in equilibrium, and it refers only to the dynamics of the system. So what I want to talk about today is basically quantum coherent versions of this second idea of this using Floquet driving to induce fundamentally new dynamical phenomena that just simply would not exist in static equilibrium because they have something to do with the motion of the system. And as we've heard many times, the context will be to consider some Hamiltonian that returns to itself after some period t. And we can frequently think in terms of the time evolution operator for one period, which upon iterating gives us the long time properties. And what I mean by quantum coherent behavior in this talk, I'll focus mainly on topological phenomena. So topological phenomena of quantum dynamics. And the reason is that, one reason is that topological properties are in some sense purely quantum phenomena. They are robust properties that rely on quantum interference and entanglement. And so we've actually heard a couple examples of how Floquet engineering could induce topology. And so one example is that you could drive your system and effectively, say, start with a trivial band insulator and effectively invert its band in some rotating frame picture and turn it into a topological insulator. Or, and what I think is maybe a completely more open direction, is to try to induce some unitary evolution that can't be described by simple static Hamiltonian, but requires some dynamics. And this opens the door to new phases, new topological phases of matter with dynamical properties that would cease if you turn the drive off. So they require this non-equilibrium drive. And so Kurt alluded to, in his last talk, this idea of a Floquet symmetry-protected topological phase of a spin chain. So here I'll draw just a little cartoon. So where the bulk, nothing much is happening. But what happens at the edge in this particular example is that the edge states undergo some topologically protected spin echo process in which they dynamically decouple from the bulk, even though nominally they're interacting with it. And this allows these edge states to, in a many-body localized and isolated setting, to perfectly store quantum information indefinitely, in principle. Yeah.
So do you mean U of t is not equal to e power minus I h f t, or do you mean that it's not equal to something?
So you can always write it as a time-ordered product of some, stacking up the evolutions for each piece of your time evolution. But the question is whether you can write that cumulative action as just, turning on some other effective static Hamiltonian, leaving it on for some time period t. And in these examples, you can. So you could just, your h effective just has a different topological invariant than the instantaneous h that you were driving with, perhaps. But for these dynamical, like this Floquet SBTs, there's no way to write the time evolution in a system with boundaries as a local Hamiltonian evolution. Yeah.
So the kind of equilibrium topological phase have boundary modes and the system spine can have tunneling through the ball. We don't split and the degenerate system.
Indeed. So the very closely analogous situation here is that so suppose you stored some information in this edge state. Its coherence time would basically be as long as it takes to tunnel through all these localized states and talk to the other topological edge mode. So it would be like exponential in system size. Just like the quantum Hall conductance is only quantized to exponential accuracy in system size. So if you like, it's like a quantum self-error correcting code that gets you exponential improvement in coherence time with the number of spins that I encoded in. OK, so I like to, this is a big open area that's just being started to be explored. So I want to set a definitive and concrete goal, which is to, take the first steps into this new arena and just, scout out what kind of phases could be there in principle. So I want to ask the formal theoretical question of, can we classify what new Floquet topological phases could occur? And then, I'll leave the, obviously important questions of how you might realize them experimentally or maybe use them for some functionality. Maybe that can happen for next SPICE conference. And I will also want to focus on strongly interacting systems. And the reason is that interacting many body systems can exhibit like really new collective phenomena that are simply not possible in a free particle setting. So familiar examples are things like Mott insulators or any kind of insulating phases of bosons or spins. And most notably is you can get emergent behavior like anyons and things or fractional quantum Hall kind of physics which rely on interactions. So I want to look at what new kind of interacting physics can come out in a periodically driven context. And so the obvious objection, which we've heard many times, is that if you drive a generic interacting many-body system, it's just going to heat up to some featureless infinite temperature state unless it can dump that energy into some bath. We've heard kind of two ways out of this conundrum. And the one I'd like to concentrate on, like the previous talks, is this idea of using disorder to prevent the relaxation to thermal equilibrium, which is believed to enable you to drive the system in a way that you just coherently dress the system, even though it's many-body, even though it's interacting. And the interesting thing is that you can get new phases of matter without cooling. And these phases of matter have quantum coherent properties, even though they're highly excited. And I just want to throw out an alternative which doesn't require disorder, which is in some sense, if you drive quickly enough, you can live exponentially long before heating up, even in the absence of disorder. And in this case, you need some effective cooling in some technical sense, which I don't want to go into. But there are fewer limitations, like you don't need disorder, and in some cases that can be advantageous. So for this talk, I'll just really think of interacting, many-body localized, and Floquet-driven systems. And we heard a bit of what could happen about this for topological Floquet phases in the last talk. And a nice way to summarize what happens in low dimensions, like 1 dimension, is that you can understand all the new phases that come out by thinking of discrete time translation, the periodicity of your Floquet drive, as effective extra symmetry. So for example, in this time crystal example, you can think of the discrete time translation as a symmetry which gets broken in the time in the time crystal phase, just like the magnet would break, time reversal symmetry. And you can put it on the same footing as equilibrium ground state symmetry breaking order. And for these kind of examples, you can use, if you want to look at topological phases, you can use well-developed equilibrium methods such as group cohomology methods and other kind of mathematical tools for classifying these topological phases. And the structure that emerges is that what you can get in one dimension is if you have a symmetry, the new Floquet phases that you get out are basically ones where you pump a symmetry charge onto the edge of your system during every Floquet drive. So for example, in this, you could take a system with just a Z2 symmetry with flipping spins up to down. And you could have a Floquet SPT phase where you flip the edge spin from up to down and back every drive. And you can think of this as pumping like a Z2 symmetry charge onto the end at every period. And since the symmetry charges of a discrete symmetry are discrete, they can only be plus or minus 1 for this system. This amount of charge that you pump is topologically quantized and can't be messed up by small perturbations. In higher dimensions, you can get even more interesting examples, such as you can get systems where even though they're made out of bosons or fermions, the emergent excitations are exotic things like anyons with fractional statistics or fractional charge. And you can get new dynamical phases where these anyons undergo some non-trivial dynamics. So I'm just kind of advertising these, but I won't. But actually, today I want to talk about a different class of phases where you can't just think of the Floquet drive as an extra time translation symmetry. And you get brand new physics that is completely different than anything that would happen in equilibrium. And these, I'll talk about two different cases, one in 2 dimensions, which are the possibility of getting chiral edge dynamics without Chern number. And I want to pick up where Nate left off earlier and talk about how to understand interacting versions of these systems from the perspective of quantum information. And it turns out that using quantum information tools, we can get a nice classification of these and a nice physical picture of what's going on. And it allows us to generalize the constructions to strongly interacting and fermion systems and boson systems, and even look at fractional versions of what was discussed in this free fermion context. And then, if there's time at the end, I want to look at how these new sets of 2D chiral phases enables new 3D topological insulating-like phases with protected surface states. OK, great. So I just want to remind you a bit about this nice model that Mark Rudner and company cooked up, which shows chiral edge motion without any bulk Chern number. And the idea is just, as Nate told us before, to apply this 4-step sequence where I start with fermions on, say, a square lattice. And on each time I draw one of these blue bonds, I'm basically turning on a hopping term between the sites of the bonds for the exact amount of time for the fermion to hop from one site to the other. And I apply it in these chiral sequence. And as we saw a couple talks ago, what happens is that if you have a fermion in the bulk, it just traces a loop and comes back to its original position. But the fermions at the edge get kind of pumped around the edge as the system goes in big open orbits. So you can effectively describe the time evolution of this system as 1 in the bulk, because everything returns to itself, and a pure chiral translation around the edge, which I'll denote as t hat. And in the absence of interactions, we can just draw a Floquet band structure for these things, and you'll see a chiral mode that winds both in the quasi-momentum and the quasi-energy direction. And the bulk bands, because they have no motion, are basically just a flat line that you can then add disorder and localize. And you could go further and characterize the topological properties of this by looking at this particular winding number of your single particle Floquet evolution, which is always an integer, which tells you basically how many of these wrappings you have. OK, so I want to ask a pretty simple but kind of puzzling question, which is, what happens if I just replace all the fermions in my models by bosons or spins? And then I could do a similar model where instead of allowing these fermions to hop, I just swap the state of the spins on 2 neighboring sites of these blue things. And then if you look in real space, the state, if I like trace the state of a spin initially here, it'll come back to itself. But the state of the spin along the edge gets transferred again. But now I face a conundrum because if I try to understand this spin system, which is inherently interacting, I'm not allowed to use a band structure picture, right? There's no sense of band structure. So how do I define, how do I understand with this apparent like chiral motion at the edge without referencing a band structure? So what I want to do is figure out how to define the topological invariant for these chiral phases without resting on the crutch of band theory. So for example, in the quantum Hall effect, we know that you can define the Hall conductance just by threading a flux through your system and seeing how much charge moves from the inside to the outside of an annulus. And that doesn't refer to some band structure picture, although it meshes up well with the Chern number that you could have calculated. And this allows you to define Hall conductance even in interacting systems. So why do I want to look at an interacting version of this? So unlike in equilibrium, even if you have a non-interacting system or a weakly interacting system, since there's no up or down to Floquet energy, right? There's no reason to fill some Floquet bands and not others, right? So characterizing the topology of bands is not immediately obviously connected to the physical properties of the system. The second is, as I mentioned in the previous slide, you can try to write down interacting versions like with bosons or spins, or you might ask, are there fractional versions of these? And none of those would be described by a band structure. OK, so how can we go about doing this? So one suggestion is like in the quantum Hall effect, if you have these chiral modes, you have an edge current whose transport coefficients are quantized. And maybe a couple of talks ago, we heard some clever ideas of how you might expose some version of this quantized edge current in particular setups. But I want to argue that generically, the edge current is simply not quantized in this chiral, from these chiral edges. And it's a pretty simple argument, right? So if I have a particle here and I evolve for one period, it moves and I get some current across here. But if I look over here, there's no particle and there's no current, right? So the amount of current that I see at any given time depends on the state that I'm looking at. And it's not quantized, and it's not topological invariant, at least in the usual sense. And what's more is that if I look at a boson or a spin system, there may not even be a notion of a conserved charge or spin to define a current for. But nevertheless, we still expect this chiral edge motion to be something topological. OK. So the way I want to propose is that if you look at a site where you have a particle to your right and evolve for one period, it'll move. If you look where there's no particle, then no particle moves. So one way to think about this is that the information about the site to your right is transferred to the site to your left, like the information about whether the site is occupied or empty. So can we make this kind of intuitive notion a bit more precise? Because, for example, if we move away from this ideal limit, where you precisely hop one particle and you allow particles to kind of weakly interact or move a little bit non-ideally, the information will both move along the edge but also spread out a bit. So to make this notion precise, we need to define a way to measure how much quantum information is transferred in a 1D system. And so luckily, there's a very nice work by Gross and company where they define a precise way to measure this quantity. So suppose I look at the 1D chain, like maybe the edge of this chiral, of this 2D chiral phase, and I want to look at a cut in the chain, and then I'll look at a region on the right and the left of this cut, and I want to make these regions big enough that if if I time evolve for one period, the information can either move across this cut or spread out, but it can't spread across the entire size of, past the edge of the region that I'm looking at. And then intuitively, what we expect is if you have a time evolution that just moves every state over one, then if I measure everything I can measure about the right side, after one period, I can construct one state's worth of information about what was going on in the left side. So that turns out to be a useful way to think about. So this will get a bit formal, but the way to codify this notion is to define a complete basis for, say, the left side, let's say with states I. And you can define arbitrary operators that change the state from I to j. Let's call them Eij. And every observation I can make on the left side is made out of linear superposition of some of these operators. And this forms an algebra because I can multiply and add these things together. And I can go further and define the overlap of two different algebras, which will basically tell us like how much can the measurements of one type of algebra tell me about the other one. So this expression is a bit messy, but basically what you do is you take the basis for this first algebra, Ea, and take its trace inner product with the basis elements of the other one, sum over all possible basis elements, and square it and take the square root. And this normalization out front fixes the overlap to be 1 if A and B are totally separate so that they commute with each other, and the dimension of A if A and B are the same. So if I take the log of this quantity, so log of 1 is 0, and log of dA is basically, so you can interpret this as like how much information about A is contained in B. OK, so with these ingredients in mind, we can now make a precise notion of this quantum information flow. So we can take all observables over here and evolve them for one time step. And suppose that sends things to the right. So then we can look at how this time evolves algebra from the left overlaps with stuff on the right. And we can divide this by the reverse process, where we evolve the algebra on the right and measure how much of it gets overlapped with the things on the left. And what these guys showed was that actually the ratio of these two things is a ratio of two integers. So it's a rational number. And this characterizes basically the imbalance of how much information is flowing right versus how much is flowing left. Yeah.
Can you think of this in terms of partial transpose and negativity?
Sorry?
Can I think of this in terms of partial transpose and negativity?
I don't know how to think of it that way, but I don't know that you can't. Yeah, maybe we can talk afterwards. I'm not sure I know the definitions of those concepts. So, but it's kind of like an overlap, but for operators instead of states.
But it's a swap, right? So this tunneling is basically you take the spin from this side, and then you swap it from the other side, and then you.
This is for any kind of evolution, basically. I didn't say what U was, but I have in mind obviously this chiral unitary motion. Okay. So the other interesting thing, about this quantity is the imbalance of information flowing right versus left is actually trivial, or 1 in this index, for any one-dimensional system. And this is actually easy to see because if you have a one-dimensional Hamiltonian, I could just stop it past some boundary. And if I had more information flowing right than left, I'd kind of pile up quantum states on the right side of my system and deplete them from the left side of my system. But all time evolutions are unitary, so they preserve the size of my Hilbert space. So this could never happen. The other thing that you can show is that if you look at this simple 4-step model, that so if you have a localized bulk, you can kind of ignore the action of the evolution in the bulk because everything's coming back to itself. And instead, you can focus on the only non-trivial part of the action, which is in the thin strip around the edge where stuff is moving chirally. And so this stuff around the edge defines an effective one-dimensional system, although a weird one because it has to be at the boundary of a 2D system. And there, this edge is basically transfers. If I have p states per site, it's the translation operator on these p states. And the index of this edge motion is just p, which is not 1. So you get an index that's different than it could be in any one-dimensional system.
But how can you define system 1 and 2 if it's a boundary of the 2D system?
So the crucial part is that the bulk needs to be many-body localized. And then this emergent L-bit picture, this emergent integrability lets you formally divide the motion of the bulk and the edge. Intuitively, basically everything in the bulk is stuck. And doesn't evolve at all. So you can basically, only non-trivial action of this will occur at the edge. Yeah.
So the difference between the case 1 and 2 is that in the first case you consider only open ends, you do not allow the periodic 1D system.
Yeah, but even if I have a periodic chain in one dimension, I couldn't get a non-trivial value of this index. So the reason that it is allowed into the edge of 2 dimension is that you can never expose a edge of this 1D boundary, right? Because the boundary of a 2-dimensional system doesn't have a boundary itself. But if I have a local 1-dimensional Hamiltonian, I can always just truncate it to some region. And this would cause basically an anomalous pileup at the ends if it had a non-trivial index. It's basically the similar argument to saying like why you couldn't have a chiral edge in just 1D for the quantum Hall states. Yeah, the other thing you can see is that you can actually realize any value of this. So remember, this index was disaster. Sorry, was quantized to a ratio of 2 integers, so some rational number. So you can get any value of this by just having a p-state model moving to the right at the edge and a q-state model moving to the left at the edge. And what's more is that no matter what I do to the edge, so if I apply any perturbation to the edge, it turns out that I can't change the value of this index nu. So this is really a topological invariant of this edge motion. And finally, you can show, as we did in this paper, that this is actually a complete classification of 2-dimensional systems with bosonic excitations and no like fractional things like anyons coming out. OK, so let me just take a step back and compare this new kind of exotic index to something we're more familiar with, which is just the Hall conductance. So the quantum Hall effect has many like pictorial similarities to these chiral Floquet phases, right? There's kind of not much going on in the bulk. There's some chiral motion at the edge. So I really want to kind of just take a step and contrast what's different about these two, besides the obvious point that one is driven and one is equilibrium. So first is that the Hall conductance basically talks about the continuous flow of charge and heat around the boundary of your sample. Whereas in this chiral Floquet phase, you have a transfer at the edge of discrete packets of quantum information. Right? So it's discrete versus continuous in some sense. The other thing is that there's a very different structure of the topological invariants governing them. So for example, the Chern number is an integer, right? And if I take 2 quantum Hall states and just layer them on top of each other, the Hall conductance just adds, right? And so, in fact, if I have an integer quantum Hall effect, there's one root state with Chern number 1 that I can make any Hall conductance just by stacking up a bunch of these things. I can get any integer. So formally, if I take 2 Hamiltonians and compute the Chern number of like this tensor product of those 2 Hilbert spaces, I just get the sum of these 2 Chern numbers. Like 2 right-moving Hall states and 1 left-moving Hall states make something equivalent to Chern number 1. OK, all pretty trivial, but I just want to lay it out because it'll be very different in this chiral Floquet case. So in this chiral Floquet phases, this chiral unitary invariant nu that I've been discussing takes rational values, not integer values. So it's already a fraction. And if I combine 2 different chiral Floquet phases together, their invariants actually multiply, right? Because their invariant is telling you how many quantum states worth of information are moving to the right versus to the left. And if I take a spin half and another spin half, the number of states multiply. They don't add. OK, spin half is a bad example because 2 plus 2 and 2 times 2 are the same. But hopefully you get the point. So like basically, if I take a 2-state version of this bosonic swap model that moves things 2 states to the right and put it on top of a 3-state one going to the left, the overall invariant will be 2/3, not 1, or not -1. OK. And in the absence of fractionalization or in boson systems, this is basically the whole story for 2D. OK. So any questions before I move on to more complicated generalizations? Yeah.
So you had a formula for non-interacting particles, right?
Yeah.
So why can't I just do the usual flux? Like if I want to do it for many-body phases, I change kx and ky.
Yeah.
Flux is called.
So firstly, that formula is defined in terms of the single particle Floquet evolution.
But that's the same as like you define many-body Chern number for the interactive for fractional quantum Hall effect.
Yeah.
So instead of integrating over kx, you just change your boundary condition. You can still define evolution operator for the entire system.
But the formula requires charge conservation, requires C1 symptom. Because you're basically twisting the boundary conditions.
But does it actually work?
Yeah, but let's say it's okay. Let's look at systems which have conserved V1. Formula, I think I can still do the same trick.
Yeah, I think it should work.
So the question is, will it give the same number as Andrew tells us?
Well, that number will be, there's a translation. So the fermions will give you 2 for this nu because each site can be either occupied or empty. And so there's 2 states that get transferred along the edge. So a 1 in that winding number gives you 2 in this nu. But like if you had 3 states that are moving, you transfer 3 states worth of information per period. So the nu would be 3 in the boson case.
I think with the cases with charge conservation, it should give the same.
For the free firm, for the
For the things that are connected to the free fermion.
No, but it's not connected. Like it can be interacting, like analog.
It could be
fraction.
interacting, but the question is, what phase do you get when you turn off the interaction? Is it do you get the non-interacting disordered phase? What's the?
No, but I want to get something that's not connected to non-interacting.
So actually we have 10 minutes.
Yeah, maybe, yeah, sorry, including questions. Yeah, let's save this for the discussion then. Okay, so let me pick up the speed a little bit, or just decrease the details and advertise 2 generalizations of this. So far I've talked about bosonic or spin systems with no topological order. You can generalize this to systems with fermions, or you can ask, can I induce fractional versions of this where I have emergent anion excitations, and can I get fractional versions of this chiral Floquet invariant? So the answer to both is yes. So let me start with the easier one, which is just fermions. So let me suppose I have a system of fermions in a superconductor, let's say. And in a superconductor, I can think of every fermion as a bound pair of like 2 Majorana fermions. Let me call them gamma I and gamma J. And let me draw these Majorana fermions as dots and put them on a square grid. And now I can do something simple, which is just to apply the same 4-step drive, but now where these blue dots basically allow the Majorana fermions to swap with each other. Right, so still a non-interacting fermion Hamiltonian. So now you might think that, well, since 2 Majorana fermions make up a regular fermion, and that regular fermion has 2 states, then each of those Majoranas has kind of square root 2 states, right? So if you think of how much information is transferred along the edge, you would think this index would be square root of 2. And you would be right in this hypothetical situation. So you can formalize this by generalizing this unitary index to fermionic systems, which takes a bit of work because you have to generalize these algebraic things to non-commuting algebras because fermions don't commute. But it can be done. So this is kind of an obvious generalization. What's kind of surprising is if you look at the physics at the edge of this phase. So let me start with a state. Let's wrap my Majorana model onto a cylinder. And suppose my initial state is one that, so whenever I draw this red line, it means that the fermion shared by these 2 Majoranas is occupied, let's say. And now let's evolve for 1 period. Everything will shift around the edge by 1 unit, right? And these red lines will move over. So if I unfold the edge and look at it in 1 dimensions, or if I cut the edge open and look at this top thing in 1 dimensions, then you can see before I translate it, I had a trivial state. And after I translate it, I have these unpaired Majorana fermions at the edge. So basically, this translation operator has switched the topological and trivial phases of the edge. And this has some consequences if I stick a vortex, a superconducting vortex, into the system. And the vortices carry, pi flux in the sense that if fermion circles them, it gets a minus sign. And it turns out that in a topological phase, if I take a ring of the Kitaev's topological wire and stick a vortex into it, it changes the fermion parity of the ground state of this ring. So it basically pumps a fermion onto this ring. OK, so now let me take my system and unfold it back onto a square. And let's suppose I have 3 vortices inside of it. And then I time evolve for 1 period, and everything moves around the edge. The edge, say, was initially trivial. Now it's in a topological state. But it has an odd vorticity inside of it. So what happens is each of these vortex will acquire a fermion, and the remaining odd guy will get deposited onto the edge. So what you have is, as you oscillate, these vortices will kind of trap and untrap fermions periodically in time. So this is actually a two-dimensional Floquet symmetry-protected topological phase. But the precise characterization is this. And what's interesting is that the chiral motion at the edge is tied to this bulk action of these vortices trapping and untrapping fermions in a periodic fashion. So you can't get one without the other and vice versa in 2 dimensions. OK, and maybe I'll be brief, but you can also get the same behavior where you have a irrational number of quantum states transferred on the edge in a model without microscopic fermions. So you can start with a model with only spins, and you can create a drive that fractionalizes this spin into a pair of emergent fermions that are kind of glued back together by an emergent gauge electric field. And these superconducting vortices become the flux of the magnetic flux of this emergent gauge field. And you can write down a simple solvable model, which I guess I shouldn't go into in too much detail, where you just have spins on a honeycomb lattice, like was originally written down by Kitaev. And you can color the bonds X, Y, and Z in this fashion. And you can apply these an SX term on the X bond, and then similarly a YY term on the Y bond, and so forth on the Z term. And I apply these 3 steps in sequence over and over again periodically. And what happens is that these fractional fermions that emerge from these spins get pumped chirally around the edge, and you can get this nu equals √2 phase without any fermions in sight. So the structure of these kind of fractional versions of this chiral Floquet phases are that the drive induces some kind of a topological order with abelian anyons, so like these emergent fermions. And what the drive also does is it takes some topological defect of these emergent fermions, so like the Majorana edge state of a 1D fermion wire in the last example that I talked about. And it moves it chirally around the edge. And this non-abelian defect carries an irrational amount, generally in these models that we can construct, a square root of an integer amount chirally around the edge. So they correspond to a unitary, this chiral unitary index that's generally square root of a rational number. And we can make solvable models of all of these things, kind of generalizing this driven Kitaev honeycomb model. And they all exhibit some interesting bulk boundary correspondence where if I have a bunch of anyons here, like gauge flux is M and gauge charge is E, as I evolve over the period, the flux gets converted to charge and vice versa in a periodic fashion. This is kind of like an anyonic version of this time crystal concept. OK, and how much time do I have left?
Well, actually, you have just 2 minutes including questions, so maybe you can briefly pursue the...
Yeah, so the last part I just will give a 1-slide sneak preview. So the idea is that if you have a 2-dimensional chiral phase, they're a closely related 3-dimensional topological insulator. So the familiar example is an ordinary electron TI. If I make a magnetic domain wall in its surface, I can gap out this Dirac fermion with opposite masses, and in between there'll be a chiral edge mode, which is like the edge of a quantum Hall state. So you can think of the surface of a TI as basically half a quantum Hall state. So in the Floquet setting, there are actually an infinite number of kind of different quantum Hall states for every rational number. So you can get 3-dimensional topological insulators whose surfaces are square roots, which is like the multiplicative version of half of these 2D chiral Floquet phases. And they have an interesting classification that's basically given by rational numbers modulo perfect squares. And we can make solvable models based on this decorated domain wall construction and explore their surface physics. And one notable feature of their surface physics, which, sorry, I'm just blowing through this thing, is that this emergent gauge charge flux exchanging topological order that I described in 2D, which I said always came with this chiral motion around the edge, can actually be realized without breaking time reversal. So they have new kinds of topologically ordered surface states that are anomalous. OK, so yeah, better wrap up. So thanks for your attention. And I just want to acknowledge my collaborators here, the references, if you're interested in reading more. Thanks.